So now we look at the general case of the rank nullity theorem. So we showed previously that if I have a basis like this, where the first new vectors span the kernel and the remaining ones are arbitrary. So the idea is that can I construct this sort of basis? So what I do, I first start with a basis for the kernel. Then I take any arbitrary basis for the vector space V. Now what I will do is, I'll try to push in u1 to u new into this basis by pushing out some of the v vectors. If nu is equal to n, which means the whole of v is a kernel of the transformation of the transformation T, then the rank nullity theorem holds very obviously. But in this case, I need to construct a basis v0. So what I do, I take the vector u1 and I write it as a combination of the basis vectors vi, alpha 1 v1 so on, plus alpha n vn. Now since u1 is a basis vector, it cannot be 0. So one of these alphas has to be non-zero. I'll assume that that is alpha 1 without loss of generality, or else one just reorders it without loss of generality. So this means I can write v1 as 1 over alpha 1 u1 minus alpha 2 v2 alpha n vn. Okay. Now from this what we get is that if I look at the linear span of v1 to vn, this is exactly the linear span of u1 v2 to vn. And the linear span of this is the whole vector space v. Linear span of this also should be the whole vector space v. Now how do I get this? So this is quite simple. If I have any combination of the v's, gamma 1 v1 plus so on gamma n vn, since v1 could be expressed in this form, I can write this as gamma 1 times 1 over alpha 1 u1, right? And then gamma 1 times 1 over alpha 1 minus alpha 2 v2 and so on. Okay, so this is the u1 coefficient, and then you have plus gamma 1. So v1 is getting multiplied, right? Gamma 1 times 1 over alpha 1 minus alpha 2 v2, and not only that, you have a v2 component here also. So this plus gamma 2 v2, and then so on all the way. So you have plus gamma 1 1 over alpha 1 minus alpha n plus gamma n vn. Okay, so this is nothing but a linear combination in u1 v2 till vn. Okay, so we have proved that the span of the original basis is the span of the modified basis. Now what remains to be shown is that these vectors u1 till vn are linearly independent. So assume the contrary. So assume that this set u1 till vn is linearly dependent. Okay, so what this means, that there exists some linear combination, I'll call it beta 1 u1 plus beta 2 v2 plus so on beta n vn, which adds up to 0, such that some beta I not equal to 0, any one of them at least. Now here, we already started with the fact that v1 to vn was a basis, okay? Which means that this on its own cannot add up to 0. Then v1 to vn will not be a basis because some linear combination of them from v2 to vn has added up to 0. Which means beta 1 cannot be 0. Okay, because if beta 1 is 0, it means one of these has to be non-zero, which refutes the fact that v1 to vn is a basis. Now, if beta 1 is not 0, then this implies that we can write u1 as 1 over beta 1 times, this is minus beta 2 v2 plus so on beta n vn, right? But we already showed that u1 was nothing but alpha 1 v1. That's how we expressed u1, right? So we said that there is, here it is. So u1 was some combination of alpha v1 till vn, this one. Okay, so this is alpha 1 v1 plus so on alpha n vn. Now from this, what we get here is, so on the left hand side you have only v2 to vn. Here you have v1 all the way till vn. So we can write this v1 as a combination of v2 to vn. Okay, so we have, and we already started with the assumption that alpha 1 is non-zero. So this implies alpha 1 v1 equals minus 1 by beta 1 beta 2 v2 plus so on beta n vn minus alpha 2 v2 so on minus alpha n vn. Okay, now I can group all the coefficients of v2 to vn in common, and what I get is, I get v1 equals 1 over alpha 1. Here, what do I have? The coefficient of v2 minus beta 2 by beta 1 minus alpha 2 v2 so on minus beta n by beta 1 minus alpha n vn. Okay, so this implies that from this what we get is v1 is in the span of, okay, because I had v1 here and on the right I had v2 to vn, is in the span of v2 to vn, meaning that b is linearly dependent, which violates our assumption that b was a basis, which means our assumption here is wrong and u1 v2 vn is linearly independent. Okay, so therefore we get u1 v2 vn is linearly independent, and we already showed that the span of u1 v2 to vn is nothing but the span of v1 to vn, which is the whole space. Okay, so this and this imply that u1 v2 to vn is a basis. Okay, so what we've done here is we've pushed out v1 and pushed in u1. Now you can continue this process. I'm not going to complete the whole proof. It goes on the same lines until we have pushed in all u1 to un and pushed out v1 to vn.